Hello everyone. Today we are going to talk about the shear force and bending moment analysis. So really the goal of this video lecture is that end of the class student should be able to define the shear force, normal force and bending moment, and of course identify what is the shear force and what is the bending moment, and classify different type of loading conditions and support as well as the reaction force. And we'll learn how to sketch a free body diagram and then solve a problem analytically using equilibrium equations on those free body diagram, and finally craft a shear force and bending moment diagram. So for this class I use the textbook Mechanics of Materials 10th edition as a reference. So before talking about the shear force and bending moment, let's take a look why we need to know this thing, right? Know these forces. So basically, just a simple application, mechanical engineering application. If you have this vehicle and the chassis of this vehicle experiencing a different type of loading condition on this beam, right? It looks like a beam, this structure, right? So different type of loading condition, distributed, concentrated load. So we need to know each of this component or structural element, how they're deforming or how they're behaving, right? So to understand or to better understand or design this component correctly, I think we need to understand the shear force, normal force, or bending moment. So let's take a look. If we have a structural element just like a beam, then what is the shear force? Shear force is nothing but internally induced force. So if you apply a force on a beam, and due to that force some of the internal forces developed within that beam, so that force is called as a shear force. Okay, so again, shear force is an internally induced force due to that applied force. So what is happening here when we are applying the shear force, it's this shear force, applied force, which is, let's say, P. Then due to that P, basically some of the it's try to break down that beam right here and here. So if we take a look at this cross section, the internally force developed or internal force, just like here we can see here, all the force is acting downward, shear force, right here in this diagram. If we take a look at the cross section or section along the plane of the force, applied force, so if we see that all those forces is acting downward, it's basically that shear force, right? So now we know that shear force. There is another force which is called normal force, and normal force is nothing but the force induced on that on the plane perpendicular to that applied force. If you look at this either of this cross section right here, just like this one, then you can see that normal force is acting inward, right? Acting inward, which is perpendicular, right? Perpendicular to that applied force. So the normal force is nothing but internal force along the normal direction. Again, normal force, shear force, both are internally induced force due to that applied force. Shear, just only the difference is shear is acting along that applied force and normal force is acting perpendicular that applied force. Okay. So the next thing is that bending moment. So let's take a look at this example. So if we apply the load right here, what is happening, this load is basically bending this beam, right? So if we apply the load P here, then it is bending. Now let's take a look at this section, cross section, what is happening here. So if we cut it right here, then what we see that the normal force, if this is the middle of that cross section, right? So bottom half, we see that like in this bottom portion, right? In the bottom portion we see that the normal force is acting outward, right? We see these arrows are acting outward. However, in the top portion of that beam, we see that the normal force is acting inward, right, which is under the compression. So if we take a point right here along this point, or with respect to this point, we see that bottom half is in tension and the top half is that the compression. So together tension and compression is creating a moment right here, right? So that moment is nothing but the bending moment, because due to this tension and compression, bending is happening right here. So the bending moment, excuse me, is nothing but the moment that causes the structural element to bend. Now you know how the bending occurs, right? So when you apply the load, if you take a cross section, you can see that there is a tension and compression is acting on that cross section, and due to that tension and compression, moment is developed, which is nothing but the bending moment, and ultimately that causes the bend of that beam. Okay, so now you know that shear force, normal force, and due to that shear force and normal force, how that bending moment created. So now let's take a look at the sign convention. This is really nothing but, just to help you to understand that if you solve a problem, let's say if you have a beam like this and you are applying a load, your shear force is, if you come from the left side, the shear force, you consider shear force upward is positive, okay? And then if you come from the right side, right, and then you have applied the load and you consider the shear force downward is negative. So again, this is nothing but just to, when we solve the problem using a equilibrium equation, then in that case we just have to think about which one is the positive and which one is the negative. Even though if you get the negative answer, we have to flip the sign, or we have to state that, either downward is positive or upward is negative. So we just need to make sure that we are maintaining that sign convention. But I think we can solve a lot of problems, and make sure that we are following the sign convention. But most importantly, the sign convention is important for this moment, especially bending moment. So what is happening here, if we apply the moment right here in this beam, then this moment is causing the beam to bend just like this, right? Bending downward, right? So this bending, it's called sagging, okay? And this moment is positive moment. This is a positive moment. However, if we apply a load in a beam just like this, right, what is gonna happen? It will gonna try to bend the beam like in upward direction, right? Just like this. This is a negative moment, right? And this is called hogging. So sagging is positive, hogging is negative. If we try to bend something in upward, right, and then then it is called hogging, which is negative moment. If we try to bend something downward just like this one, then we call it sagging, which is positive moment. So now let's take a look, what are the forces and moment we oftentimes see in this class. So these are the very basic the forces, right? But you could see that, combination of any of those, or only one of these loading condition. So you can have a concentrated force, right, acting only one point, and you can have a distributed force or distributed load at over a certain length of that beam, or throughout the beam. These distributed load even can be different types. So it can be uniformly varying load just like this, right, or just uniform distributed load, or this distributed load can be other type as well. For example, you can have varying distributed load, right? So, and with the distributed load, sometimes you may have a concentrated load as well. Again, there are a lot of combination a beam can experience, or a structural element can experience. But for simplicity, you need to know that concentrated load is acting only one point, distributed load is acting, so it acts over a certain length, and another force or moment, which is we call the concentrated moment, can be applied externally as well. So it can be clockwise, counterclockwise, which direction you are taking positive. It's up to you. Either clockwise is positive or counterclockwise is positive. um, so yeah, it is possible that in one single structural beam you can have a concentrated, you can have a concentrated load, you can have a applied moment, and you also can have a distributed load, right? These are the three things, or any of this combination it's possible, but we'll solve a problem using one of this combination. Before solving problem, let's talk about a little bit about the support, type of the support, because it is very important to know about the support and also the reaction force. So this is a simply supported beam. If just if the beam is laying on top of this this support right here, then there is no other reaction force, only one reaction force, which we call Ry. Okay. However, if there is a pin support right here, right, just imagine that there is a pin support right here, then we'll have a pin or hinge support. Then we'll have two type of reaction, Ry and Rx. Okay. So again, for simple support there is only, however, if there is a hinge or pin support, then we have two type of reaction, vertical and horizontal. In the roller support, where it can move this way easily, right, this horizontal direction, then there is no reaction in this direction. Okay, so there is only one reaction here, which we call Ry. For roller support, one simple rule, one reaction. Okay. And then fixed support, so we have one reaction in horizontal direction, Rx, we have another reaction in vertical direction, Ry, and also we have a moment. How? If we apply a load right here, then there is a resisting moment right here as well, so this moment, right? However, if we apply a load in pin support, this is free to rotate or free to move, right, up and down, so there is no resisting moment. In that case, roller support, we don't have any moment. Same goes to here. See, if we apply a load right here, it is also free to rotate, kind of free to rotate, it doesn't have the moment. So again, one more time, simple support, there is only one reaction. If it is a pin support or hinge support, there is two reaction, no moment. Roller support, we have only one reaction, vertical reaction. However, if we have fixed support, then we have vertical reaction, horizontal reaction, and a moment. Okay, so now we know what are the loads, what are the internally force, what are the reaction. Now we should be able to solve a problem. But even before solving a problem, let's define one more time, right? What is the shear force and why? What is the shear force diagram and bending moment diagram actually? Again, shear force is nothing but internally developed force, right? So if we plot that internally developed force, then we'll get a diagram, and that diagram is called shear force. So the shear force diagram is one which shows the variation in shear. Okay, how the shear force is varying along this beam, right? Along this beam, that representation or that diagram is known as the shear force diagram. Similarly, bending moment is nothing but how the moment is changing from point A to, let's say this is point A, this is point B, from point A to point B along this length. And those changes or variation, representation of those changes or variation is nothing but the bending moment diagram. So by looking at shear force diagram, we can say that how the shear is changing, and by looking at the bending moment diagram, we should be able to say that this is how moment is changing, and this is for this particular point moment is maximum, or for this particular point moment is minimum. So would be able to see those changes, right? So how those shear are changing. Excuse me, and this should not be okay. Okay, so we should be able to see that how those shear force is changing, right? So if it is a 0, then the shear would be something like this, and the shear force diagram. And in the moment diagram, we should be able to see that how the moment is changing, right? So this is 0 0, so this is shear and moment. Now you may wonder how I plotted this. So that's what we are going to do in this class, how to draw the shear force and bending moment diagram. Okay, so what are the steps involved in a shear force and bending moment diagram? So these are the basic steps. So the first step, when we see a problem, you have to craft or draw a free body diagram, step number 1. Okay, and then from that free body diagram, when you know that, okay, I got these reaction forces, I got all those forces, on this free body diagram, then you can apply or you can determine that reaction force and reaction moment. But how? Using that equilibrium equation, right? So you have to identify the reaction force, reaction moment, and use that equilibrium equation. You basically determine those reaction force and reaction moment. Okay, and then step 3 is, once you have that reaction force and reaction moment, then you can start work with the shear force equation and basically draw the shear force diagram, right? From the equation you can draw the shear force diagram. Similar to that, once you have the moment equation, you can draw that moment diagram. Okay, so a simple rule for the shear equation. So let me draw one thing. So if let's say this is a free body diagram and you have only a concentrated load, one single point load, right? So in that case, in the next diagram would be your shear force diagram. In that shear force diagram, change of the shear will be just that force. So that means basically there is no change, no change of the shear. However, excuse me, I think I have to write it. Okay, so the change in the shear would be just like a straight line right here, just like a straight line. However, in the moment diagram, due to that single point load, the moment would be a line, but it would be a with angle, right? Some sort of slope. So we'll see how this how to measure this slope or how to determine that slope. But let's start with, or let's at least take a look on the shear force diagram only. Now if you have in a beam, if you have a distributed load, right, just like this, then your shear force diagram will be like a straight line, just like this. However, there will be a slope, right? So let's say this is W, distributed load is W, and your shear force or applied force is F, single point force is F. Then for concentrated load, the change in the shear is the magnitude of that force. Okay, however, if you have a distributed load just like this, W, right, then your slope of this slope of the line in shear force diagram would be nothing but dV divided by dx, which is Wx, right, the distributed load. Now if I take the integration in both sides, I'm sure you all know from the the calculus class that if I take the integration, then dV, and I'm taking the dx in the other side, right here. So it would be integration of dV equals to integration of Wx times dx, right? So the integration would be nothing but a Bx equals to integration of this term plus integral constant C, right? We have to determine that integral condition using a boundary condition. We'll see how to determine that. But now you know that how to get the shear force for distributed load and also for concentrated load. Okay, so these are the two equations I want you to keep in mind. So if there is no change in the load or only single point concentrated load, the shear is equal to the applied load. However, if you have a distributed load, then the shear force V of x is equals to this equation. Okay, we'll learn how to solve this equation and plot shear force diagram. The next one is that moment equation. Again, similar to that shear, if you have a, let's say, only this is a one single point and you have a moment applied right here, there is no other moment, then moment would be nothing but, or bending moment would be nothing but the initial moment, okay, for one single point. However, if you have a moment, then moment is for distributed load, then the slope of that moment would be equals to dm over dx equals to nothing but that shear force, right? So I'm talking about this one. So if you have a distributed load right here, in the shear force diagram we saw that it would be a line with slope, right? Similar to that, if we have a just like a concentrated moment here, then in the moment diagram what we'll see that we'll have a moment with the slope, right? So in this moment with the slope, what we are gonna take a look at that from moment from, basically the steps are, first you have a loading diagram, right? Let's say this is F force, and then you get a shear force diagram, right? And then you basically, last one, you get a moment diagram, which is something like this, right? So this equation is V of x, this equation is M of x, right? So we for one single point, we already know that what is the V of x from the previous slide, right? If it is a concentrated load, then V of x is nothing but F. If it is a distributed load, V of x equals to this. Similar to that, once we get that V of x, then the next task would be moment equation, right? So how to get how can we get the M of x? Well, if it is a one single point, there is nothing but M naught, right? But if it is a distributed load, due to the distributed load, you get the slope, or for this case, you know, it is seemingly distributed shear, right? For due to that single point force. So how we can determine that M of x is taking the integral. Okay, again I'm doing the same thing, taking the integration of dm vx times dx. So if we do this integration, then again we'll get another integral integration constant c, and we have to solve it, and in that way we can determine that what is the moment at starting point, what is the moment at final point, and you know how this moment is changing along this length, which is, let's say this is x. Okay, so we can determine that. Let's take a quick problem and try to solve this problem, and basically you know, learn how to draw that shear force and bending moment diagram, right? So for this particular problem, we do see that this is a, you know, this is a beam with two different support. Point A, which is hinge support, right, or fixed, not fixed, hinge support, and point B is a roller support, right? So if we take a look on this beam and just draw the free body diagram, which is the first step, then what we're gonna do is that point A, there is two force. One is that AY, you know, vertical, and horizontal is AX. These are two reaction force. Okay, and then at point B we have roller support. For roller support, we just learned that there is only one single reaction, which is the vertical reaction BY. Okay, and now we know that reaction forces, we have to get this equivalent force due to that constant distributed load. We have the distributed load, which is W of x, right, equals to 10 kilonewton per meter. However, this distributed load is acting upon a 2 meter length, so we have to, you know, convert it in equivalent one single point load. Nothing, that would be nothing but 10 kilonewton, 10 kilonewton by meter times 2 meter, 2 meters. So meter omitted, so total would be 20 kilonewton. 20 kilonewton. So we got 20 kilonewton, which is acting in the middle of that 2 meter, right? So now we got the reaction force, we got the equivalent load. We should be able to solve it for equilibrium equation. So equilibrium equation, what we are going to do is that summation of Fy, right? So why I didn't take the Fx? You see, there was only one force right here, and that force, there is no other reaction force. So that means the Ax is automatically 0. So that's why I didn't take f of x. We don't need this one, okay? However, Ax equals to already 0. So however, for y direction we have two force, right? Actually three force, but we have two unknown, and we need to have two equations so that we can solve this two unknown, okay? So the first, f of y, I'm thinking about vertically upward direction is positive, then ay plus by minus 20 kilonewton downward is negative equals to 0. So I got one equation but two unknown, okay? So to solve this equation I need another equation. So two equation, two unknown, I think easily solve it, right? So to get another equation, what I'm going to use is that moment equation, and moment equation clockwise is positive, okay? I'm applying the moment at point B right here. So we can do either point A and point B. So let's just take a moment at point B. What is going to happen is that with respect to point B, AY is creating a positive moment, okay? Because this is clockwise. So AY times total distance is 8 meter right here from this point to this point, okay? Now this 20 kilonewton is creating the negative moment, which is counterclockwise, okay? So we have 4 meter times 4 meter plus 1 meter right here, right? 1 meter right here. So that means 5 meters. So 20 times 5 equals to 0. So from this equation I can solve the AY, which is 12.5 kilonewton. Well, if you apply the 20 kilonewton from the top, and one is 12.5 kilonewton right here, then other would be 7.5 kilonewton, right? Or simply just plug in this value in this equation. That's it. You would get AY and BY. So now at this point, what we did, we drew a free body diagram. We used this equilibrium equation, and we calculated that reaction force, okay? So number 3 step would be that plotting that shear force diagram. But how can I do that? First we need that shear force equation. Using that equation we can draw the diagram, okay? So let's start with the point A. At point A, in what we saw, point A, there is two reaction, but we saw that Ax equals to 0 because there is no other resisting force. So the AY, we got AY equals to 12.5 kilonewton, okay, at point A. So there is no other load applied in point A. That means that the shear is nothing but the applied force or the reaction force, which was F, right, or AY right here, 12.5 kilonewton. So at point A we got 12.5 kilonewton positive shear, which is going upward right here, okay? So this is 12.5 kilonewton. Now from point A to 2 meter, and in this point right here, in this point we don't see any other applied load. So there is no external load, right? There is no change. So that means there will be a straight line right here, which is also 12.5 kilonewton. So there is no change, right? So this is a straight line. Excuse me. So segment, there is no changing, it would be same shear. However, from this 2 meter to 4 meter in this point, we do see that there was initially a distributed load, right? So distributed load. Now due to the distributed load, we have to get a shear force line which will have a slope, right? So for the distributed load, if we just go back a little bit, if we have a distributed load, we know that shear equation V of x equals to this, right? Integration of Wx times dx plus c. So just take that equation and then solve it. So for this distributed load, we know that slope dv by dx equals to w, right? Which is nothing but the distributed load. So v of x equals to w times dx plus c. We know this equation. So in that case, w initially distributed load was 10 kilonewton. However, I'm taking shear force upward is positive, right? Upward is positive, and applied this distributed load was initially it was downward, right? 10 kilonewton per meter, and it was downward, that's why it would be negative right here. So 10 times dx plus c. So we get this, if we do this integration, then it would be 10x plus c. Okay, however, we don't know the c, that's why we don't know what is the value of the shear, right? We know the shear force at this point, which is still 12.5 kilonewton. However, after this point, the shear force is changing. Okay, so at this point, x equals to, right here, x equals to 2, right? So at x equals to, when x equals to 2 meter, then we know that shear force was 12.5. So just plugging in these values, 12.5 equals to 10 times 2 plus c, then we'll get the c value constant, integration constant 32.5. Okay, we got the shear equation. We know that constant value on this equation. Now let's change the x value along this portion or this line, then we'll simply be able to determine that how the shear force is changing. Okay, so this is the shear equation. Would like to see what is the shear at point when x equals to 4 meter. Okay, so this would be total x equals to 4 meter right here. Okay, so at x equals to 4, if we plug in v of x equals to 4, then 10 times negative 10 times 4 plus 32.5, which is negative 7.5 kilonewton. Look, here was 12.5 kilonewton, but when we are coming at point x equals to 4 meter, then it is negative 7.5, right? Negative 7.5. That means it's downward. So now the line would be changed all the way from here to here, right? Straight line, negative, fine. And the slope of this line, it would be nothing but the negative 10 kilonewton, right here. Excuse me. Okay, so we know this equation, and we know that the shear of this line. Now let's take a look from this 4 meter to point B. What is happening? Okay, so from 4 meter to point B, we don't see any applied force, right, except this reaction force, which was 7.5 as well, right? So we have to go straight because there is no change in the shear. So we coming here negative 7.5. However, by we found that positive 7.5. So the negative 7.5 kilonewton plus 7.5 kilonewton by, which is acting upward, together they're meeting at 0 or omitting at 0. So that means we started at 0 point and we finished at 0. Our shear force diagram is correct, and we crafted the right shear force diagram. So this is how you craft the shear force diagram. Okay, the next thing we would like to see, I think I already talked about that. If it is a 7.5 right here and there is no change in the shear force, that means that negative 7.5 plus we got the by equals to positive 7.5 kilonewton. So negative and positive, they're meeting at 0. And again, I just showed, just solved it, how they're meeting at 0, starting at 0 and meeting at 0. So the next thing we would like to see is that bending moment diagram. Okay, so we already crafted the shear force diagram. I think I forgot to mention one thing is that bending moment diagram, we craft this bending moment diagram from the shear force, not looking at the loading diagram anymore or free body diagram anymore. So we'll look at this shear force diagram. Okay, so at point A in the shear force diagram, what do you see? There is no applied moment at this point, external moment or applied moment, okay, because there was only simply reaction force. So that means the moment is zero. At this point, moment is zero. Okay. However, from point A to point 2 meter, right, in at this point, how this moment is changing, because the shear, there is a straight line of the shear, that means a flat line of the shear, that means in this diagram there will be a line with the slope, but we don't know that slope. Okay, so the slope would be nothing but the shear, equal dm divided by dx equals to the shear, and the shear from this point to this point was 12.5 kilonewton, right? So that means we have to draw a line, and that line will have a slope 12.5 kilonewton, but the slope of this one is 12.5. Since the slope is positive, it's going this way. Okay, now the question is that how much would be the value of moment at point 2, or what would be the value of the moment at point 2? We don't know that, right? So we know that equation y equals to mx, right? This equation is nothing but a straight line passing through the origin, right? And the slope is m right here. So using this equation that is passing through the origin or 0 0 position, then we'll get moment m equals to 12.5 times x. In that case, this 12.5 is the slope, right? So we know this equation would be let's say m equals to 12.5x, right? So if we plug in that to x value right here in this equation, then which is 2 meter, then we'll get the moment right here, which is 25 kilonewton meter. Okay, so we got here when x equals to 2 meter, then we have maximum moment at this point here. So now we know at point when x equals 2 meter, what about x equals to 4 meter, when total x equals to right here x equals to 4 meter, then how much would be the moment? Well, in this case, we know that shear equation, which is negative 10x plus 32.5, just from the previous the slide, then we have to take the integration of this equation, right? So we know that moment equation, m of x equals to bx times dx plus c. So if we do that integration, then we'll get this moment equation. So you have 10x square by 2, which is 5 now, and 32.5 times x plus c, right? So now we crafted a moment equation, which is very good, but we don't know what is the value of the c. Well, we know that value of the x at this point, x equals to 2, and also we know that moment, which is 25. So in this equation right here, we have to plug in those values. Okay, so let's take a look. If we plug in those values, x equals to 2, right? Let's say here 25. So when x equals to 2, right here we know that moment was 25. So that's what I'm plugging in this equation. Okay, x equals to 2, moment is 25. Then if we solve it, then we'll get c equals to negative 20. So now I got this moment equation, right? So using this moment equation, I can get the moment at point 2. So I know at point 2, and I can get the moment at point 4. So when x equals to 4 meter from this side, okay, then what would be the moment? When x equals to 4 meter, moment would be 30 kilonewton per meter. How? Just plugging in this equation, right? Minus 5 times 16 plus 32.5 times 4, negative 20, right? So if you solve this, you would get 30 kilonewton per newton meter. Okay, So that means we got here 25, even here a little bit higher, right? 30, let's say this point. Now the question is that how can we go from 25 to 30? Because it is a straight line in the previous line with the slope, so it would be a parabola in the moment diagram, right? So order of line is changing. So that means either if we can go this way, this parabola, or we can go in this parabola. Okay, which one is correct? Well, so there is a way to determine that which one is correct. Let me show you. Okay, so in these 2 points you see that the minimum is in this point and maximum is this point, right? So that means it would be slow here and then it would be fast here. So it is going to and fast here. Or actually I don't think that I'm explaining it in a good way, right? Okay, do we have extra space? Okay, so let me explain it here. So if you have a point right here and then the minimum moment is here and maximum moment is here, right? Then you can do this way or you can do this way, right? So that means this is slow and this is fast, right? This is fast and this is slow. So in that case, for minimum we have to use this slow right here, and then maximum we have to have the fast right here. However, if we have the opposite, if we have a moment line like this, we say have maximum here and then minimum, and then we have to go from this point to this way. So yes, we have to use this line, right? So for our case, we found that if we go from point this point to this point, and this is 25 and this is 30, right? So we have to go slow and then fast. Actually, I think I did it the wrong one, sorry. Yeah, okay, we have to go slow and fast. Okay, so this would be the one. So that's how we'll plot the moment. Okay, yes, so right here, okay, it would be a parabola like this. So this one would be 30, this point right here. So now from 30 to from x equals to 4 meter to point B, what we are gonna see, let's take a look. So from 4 meter in this segment to the point B, we see that there is a straight line, right? There is a straight line of the shear. That means in the moment diagram it would be a line with the slope. So in the line line with the slope, we need to determine that slope dm divided by dx is nothing but the shear force, which is negative 7.5. That means we had this, right, 25 and 30, and now we'll have a line that has the negative slope, right? We will have a line right like this, but that will have a negative slope, so which is negative 7.5. So but we don't know the equation of that line. So the equation of that line would be nothing but negative 7.5 times x plus c. And you should realize that if there is a line and it's not going through a origin, then the equation is equals to y equals to mx plus c, right? In that case, we got the slope is negative, so that's why moment equals to negative 7.x plus c. Okay, again, we don't know the c. However, we know that moment at point when x equals to 4 meter, we know that moment, right, which is 30. So x equals to 4 meter, moment is 30, and then from here we can calculate the c, right, which is 60. So now we know that moment equation, which is a straight line with the negative moment. Okay, So we from there, if we draw this one, then at point B, what would be that moment, right? So total x would be how much? 8 meter, right? So if we plug in this 8 right here, then we see that moment is 0. That means from 30 here to it is straight going to 0. It is a straight line, perfectly straight line that has the slope negative 7.5. Okay. So here we do again see that we started from the 0 moment. Here is a perfectly straight line, and then there is a parabola right here which is 30, the maximum value, and we saw that this at point B it is 0. Okay, so now we know how to from the shear force diagram we know how to draw that bending moment diagram as well, right? So this is perfectly straight line, this is a parabola line, again this would be a perfectly, actually it should be meeting here, perfectly straight line, right? Okay, so from shear we draw that bending moment diagram, right? So that would be it. So now you know that if we have a applied load on a beam, then how this shear force and bending moment diagram is basically okay. So here is the one of the important thing I would like to discuss is that, okay, by knowing this shear force and bending moment diagram, what it is going to help, or how can we predict that how would be the deformation? So here you see that all the moment is positive, right? Because everything is up, right? And if you consider this is a 0 on the baseline, all this moment 25 was positive, maximum moment which is 30 is also positive, right? So all the moment is positive. Now if you think about that sign convention I just told you, that if you have a positive moment, then your structural element is gonna bend like this. So if it is a point A, point B, right, and this is called sagging, and it does make sense perfectly. Why? It's because of initially we had, if we think about this way, the beam, we had a distributed load right here, and that distributed load will gonna bend the beam downward, which is the sagging, right? This is perfectly making sense. So yes, if you take a look at the shear force diagram, and moment diagram, and you do see that there is no positive negative moment, all the moment are positive. Yes, it is creating the sagging effect on that beam. Okay, so this is the importance of the shear force and the bending moment diagram. So again, if we have a applied load on this structural element, then it will try to bend like this, okay, due to that load. So that's all from today's class. We talked about a couple of things I would like to mention. We talked about the shear, right? We talked about normal force. We talked about the free body diagram. We talked about the reaction, right? We talked about the equilibrium equation and determined that reaction, and we also talked about this shear force diagram and bending moment diagram. Well, that's all from today's class. We'll look forward to the next class. Thank you.